This is the fourth module in a series of modules where we are discussing examples of contour integrals. So far we discussed simple examples, but in this module we are going to input another difficulty in our calculation, and which is if a branch cut passes through our contour. So how we are going to calculate that contour integral. Now let's see what we have calculated so far. In example 1 we evaluated this contour integral along this contour C1, and then the function was the same but the contour was different and it was C2, and in both cases the answer was 0. And in the second example we calculated these two contour integrals, and in the first case the answer was iota pi, and in the second case the answer was 0. Although the contour C1 and C2 was the same, but the answer was different. And in the third example we evaluated this contour integral, and in this case the contour C was a simple closed curve starting from minus iota, moving in a counterclockwise direction and ending again at minus iota. Now these examples gave us the following questions. So the first question was when a contour integral is independent of path, and the second question that we want to explore further in our future discussions is when a contour integral around a simple closed curve is 0. So these kind of questions will be answered in a much detailed way in our future modules. Now in this module we are going to focus on how do we calculate a contour integral if a branch cut passes through our contour. Now there are much more complicated examples of this kind of contour integrals where a branch cut passes through our contour, but we are going to consider a very simple situations, but these simple situations will give us two different ways of dealing with these kind of contour integrals, and of course the same idea can be applied in difficult situations. Now let's begin with our example. Now the function that we want to evaluate or integrate is z raised to power a, and the contour is basically a semicircle from 2 to minus 2, and we are moving in a counterclockwise direction. Now as you can see in the diagram. Now we know that how do we define this exponential function z raised to power a. So this is equal to e raised to power a log of z. Okay, and we know that how do we define log of z. So this is equal to natural log of the modulus of z plus iota argument of z, and we know that argument of z is basically a multivalued function, and hence this log z is a multivalued function. Now we can calculate its principal branch, and in this case the principal branch is given in like this, and so when I say in this case it means we are taking the branch cut to be the negative real axis, and of course we can take any ray to be the branch cut, but in this case we choose this branch cut to be the negative real axis so that the branch cut intersects our contour. Now once again we can say that we have created a situation where the contour passes through the branch cut, and in some cases it is very much unavoidable so that the contour passes through a branch cut, but in this case it's a simple example and we have created a scenario where the branch cut passes through the contour. Now if we take this principal value of logarithm, then the principal value of this exponential function becomes e raised to power a principal logarithm of z, and of course this principal log varies between minus pi and pi, and this gives us the principal branch of this exponential function. Now why we are interested in these branches? Okay, because we want to integrate function f of z of t, z prime of t, and we know from our discussion where we considered how to integrate a complex valued function of a real variable t, and in that discussion we observed that this integration is only possible when the integrand is a piecewise continuous function, and we also know that along the branch cut this function is not continuous. So that's why we are focusing only on one branch of this function, of this exponential function z raised to power a. Okay, so and in this case, of course, we consider the principal branch. And what will happen? So along this minus pi, or you can say along the line negative real axis, this function logarithm is not going to be continuous. So that's the kind of difficulty we are going to be dealing with when we want to evaluate this contour integral, that along the negative real axis, okay, so along the negative real axis we have a point of discontinuity, and of course this point, which is basically -2, is part of the contour. So if this happens, how we are going to evaluate? Because if this function, okay, so f of z of t, z prime of t dt, so if this integrand is not continuous, is not piecewise continuous, then it is not possible to integrate this function. And of course in this case the function f of z is z raised to power a. So all our effort is on making this function to be piecewise continuous, or try to find another method where we can avoid this situation. Okay, so now the overall scenario is we have a contour which is semicircle from 2 to -2, moving in counterclockwise direction, and this contour passes through the branch cut of the function z raised to power a. Now there are two methods for dealing with these kind of contour integrals. Now let's focus on the method number 1. In this method we'll use the concept of a limit. So how we are going to use that concept of limit? So what we do is basically we take the contour from 2 to this point such that this point corresponds to the angle gamma. Okay, so in other words we take this contour C prime defined in the following way: z of t is equal to 2 e raised to power iota theta. Now the parametric equation is the same, but the variation of theta is taken less than or equal to gamma, greater than or equal to 0. So we start from 0, but we, instead of ending at pi, we end at gamma, and gamma is some angle between 0 and pi. Okay, and of course what are we going to do? So when we evaluate this contour integral along this contour C prime, then in the last step we will take the limit gamma approaches to pi. Okay, and when we take this limit, then we will be getting our required answer. Now why this technique is effective? So this technique is effective because there is no branch cut on the contour C prime, because we are avoiding this point theta is equal to pi, which is basically the point of intersection of this contour and the branch cut. So we just avoided that point and taking this gamma to be some point which is strictly less than pi and greater than 0. So gamma is some point between 0 and pi. Okay, and what are we going to do? So let me write down aim here. So the aim is to evaluate this integral along this contour C prime. Okay, so this z raised to power a dz, and then take the limit gamma approaches to pi, and this is going to give us the contour integral z raised to power a dz along the contour C, which is our required contour integral. Okay, now let's begin with our calculation. Okay, so C prime z raised to power a dz is going to be equal to, now the variation of this theta is going to be from 0 to gamma. Okay, and this is f of z of t. So what is the function? Function is z raised to power a, so we just take the power of 2 e raised to power iota theta to be a. And what is z prime of t? So we can easily calculate, it's 2 iota e raised to power iota theta. So that's what we want to evaluate. Now we don't have to worry about anything about the discontinuity of this integrand, because we have taken care of that by taking gamma to be less than pi. So this is piecewise continuous. We can integrate it. Now simplifying it further, 2 raised to power a plus 1 iota, so it will be out of the integrand, integral sign, so 0 to gamma e raised to power iota a plus 1 theta d theta. Now let's integrate this function a plus 1 iota. So this is going to be iota e raised to power iota a plus 1 theta divided by a plus 1 iota 0 to gamma. Okay, now let's move on and apply the limits of integration. Okay, so if we apply the limits of integration, so what do we get? 2 a plus 1 iota divided by a plus 1 iota, so e raised to power iota a plus 1 gamma minus e raised to power 0. So simplifying further, so what do we get? 2 raised to power a plus 1 divided by a plus 1 e raised to power iota a plus 1 gamma minus 1. Okay, now this is basically the integral along the curve C prime. The function is z raised to power a dz, which was very simple to evaluate. Now if we want to calculate the contour integral along the contour C, then we use the limit. Okay, now let's use the limit. So in this case we just take the limit, gamma approaches to pi, so z raised to power a dz c, so this is going to be equal to gamma approaches to pi 2 raised to power a plus 1 divided by a plus 1 e raised to power iota a plus 1 gamma minus 1. Now of course this 2 raised to power a plus 1 over a plus 1 can be written outside this limit, and when we take this limit gamma approaches to pi, then this becomes e raised to power iota a plus 1 pi minus 1. So that's basically the value of this contour integral. And of course if a is an integer, so what are we going to get? Okay, so if a is integer, so this is just a particular case of this contour integral, so we are going to get the following thing. So c z raised to power a dz is going to be equal to 2 raised to power a plus 1 divided by a plus 1, and when we evaluate this thing, then this is going to be equal to cosine a plus 1 pi plus sine a plus 1 pi. Okay, so that's the value of this e raised to power iota a plus 1 pi minus 1. And we know that if a is an integer, then a plus 1 is an integer, and sine integer multiplied by pi is basically 0, so this term is 0. And we also know that if this is an integer, then cosine of a plus 1 pi becomes minus 1 raised to power a plus 1. So the answer in this case is going to be equal to 2 raised to power a plus 1 divided by a plus 1 minus 1 raised to power a plus 1 minus 1. So this is the answer in the case if we use this limit. So now let's move on and let's see if there is another way of calculating this contour integral. So remember, a branch cut passes through our contour. Okay, now we know that. Okay, so what do we want to evaluate? So dz and c is basically z of t is going to be equal to 2 e raised to power iota theta, and theta lies between pi and 0. And we also know that f of z dz along this c is equal to a to b if this is the variation of the parameter f of z of t z prime of t dt. And what is our main focus? Our main focus is try to avoid the situation where this integrand is not piecewise continuous. Okay, so in this second method, what do? Now we assign value assign value to f of z of t, z prime of t. Okay, so at t is equal to pi. So this is the point t is equal to pi, such that this function f of z of t, z prime of t is piecewise continuous. So that is our main task, piecewise continuous on this closed interval 0 to pi. Okay, now let's evaluate what is the function first. So f of z of t, z of t is obviously 2 e raised to power iota theta, and f of z is z raised to power a. Okay, now using its values we can easily calculate that this is going to be equal to 2 e raised to power iota theta raised to power a. So this is f of z of t multiplied by z prime, so 2 iota e raised to power iota theta. So this is going to be equal to 2 raised to power a plus 1 iota e raised to power iota a plus 1 theta. Now we want to calculate a value. Now the point is we want that the limit, so in this case basically the left hand limit should be equal to the functional value. Now if we want that, then what do? We assign the value of the left hand limit to be the functional value. Okay, now let's see how do we do that. So we calculate this left hand limit where theta approaches to pi minus from values less than pi, and we calculate this limit 2 raised to power a plus 1 iota and e raised to power iota a plus 1 theta. So if we calculate this limit, then we easily see that the value is 2 raised to power a plus 1 iota e raised to power iota a plus 1 pi. And if we say that this is the functional value, okay, so this is basically f of z of pi, z prime of pi. So if this limit value is equal to the functional value, then everything is going to be simple. This integrand is going to be piecewise continuous and we can easily calculate its value. So that's what we did in this case. Okay, so since the functional value is equal to the left hand limit at theta is equal to pi, so this function, so f of z of t, z prime of t is left continuous. Of course it can't be two-sided continuous because there is nothing on the other side, so is left hand or left continuous, left hand continuous or continuous from the left side at theta is equal to pi. Okay, so this implies that this integral is possible. So where we take 0 to pi f of z of t, z prime of t dt can be evaluated. So since the integrand is piecewise continuous. Now let's move on. The next part is going to be much simple. Now in this case we just calculated the integral in a usual way. So now we have fixed everything, we assigned the values such that this integrand is basically piecewise continuous, and now we are just evaluating it just like we evaluate these integral. It's simple in simple situations. E raised to power iota a plus 1 theta d theta. So just integrating a plus 1, integrating this exponential function theta divided by iota a plus 1. The limits are 0 to pi. So if we apply these limits, so we are going to get 2 raised to power a plus 1 divided by a plus 1. So iota iota. So e raised to power iota a plus 1 pi minus e raised to power 0, and this is going to be equal to 2 raised to power a plus 1 divided by a plus 1 e raised to power iota a plus 1 pi minus 1. So which is the same answer that we get in method 2. Okay, so these are two different strategies for evaluating contour integral if a branch cut passes through our contour. And of course, the similar procedure can be applied. And of course, similar procedures can be applied to compute the following contour integral. Now in this case, it is complete circle from minus pi to pi, and of course, if we take the branch cut to be the negative real axis, then there is a branch cut on this contour, and we can choose either of these methods to calculate this contour integral. Now in this module, we calculated these very special examples if a branch cut passes through the contour.